Hi everyone. So in this video we discuss different types of recurrent neural networks that are used basically in the practice of deep learning. And the objective here, and that's important to note, the objective here is not to come up with an exhaustive list of all recurrent neural networks, but basically to highlight the important features specifically where the recurrence is happening and how the output like the form of the output, whether it's at every time step or at the end, and to understand how these features affect basically the difficulty or ease of optimizing the neural network, as well as the expressive power of that neural network, like is it more powerful or no. So we'll discuss three types and we'll call them type A, B, and C. Type A is basically on the left right here. So you have an input at every time step. You have hidden to hidden recurrence. So there is a connection with a one time step delay. And as we mentioned in the last video, the dashed or the shaded box, the shaded rectangle will be used to represent a delay of one time step. And then there is an output in every time step. Type B networks, basically you have an input at every time step, an output at every time step, but the recurrence is happening from the output at time t to the value of the hidden layer at time t plus 1. And the last one, type C, basically you have hidden to hidden recurrence as in type A, but the output happens only after processing the whole sequence. So you don't output unless after you process the whole sequence. The difference between outputting at every time step or outputting at the end, this is a difference in many cases, a difference in application, right? But the difference between, so you could imagine combinations, you could imagine different variations of the network that outputs at the end, right? So it doesn't have to be a hidden to hidden recurrence in that form, and the same for type A. But outputting at every time step or outputting at the end, we will see in the optimization actually how that makes a difference, right? So type A networks, the first comment that I would like to say is that type A networks are actually backed by theoretical guarantees. So there are theoretical results on the power of type A networks in simulating Turing machines. And basically what that means is that they can compute general functions, right? So these kind of networks are very powerful in a sense that they can represent a very general class of functions. And if you're curious about the details of that, you can read, other than of course reading about the background of what Turing machines are and what the Church-Turing thesis on computability is, you can check these two papers. One is called Turing Computability with Neural Nets, and the other is called On the Computational Power of Neural Nets. And both are basically papers that came in the 90s, and they were basically motivating these type A networks. But as we'll see immediately right now, these type A networks have a problem with their optimization, right? So why they are expensive in terms of optimization, in terms of both the computation time as well as the memory. The problem is that for type A networks, right, because there is the hidden layer at time 1 affects the hidden layer at time 2, and the hidden layer at time 2 affects the hidden layer at time 3, and so on, you have to wait until the end before backpropagation starts, right? Because you cannot really you have to compute the whole sequence of outputs, right? And this is the case whether actually you have the output at every time step or the output at the end. Of course, if you have the output at the end, then this is clear why you have to wait until the end. But even for type A, you still have to wait until the end of forward propagation before back propagation starts. So it's expensive in memory because I'll have to store the hidden layer values for all time steps corresponding to the whole sequence before I start backpropagation. So remember, from section 1 of this course, we remember that in order backpropagation requires storing the hidden layer activations. Here I will store the hidden layer activations of all corresponding, the vectors corresponding to all the time steps. And also in terms of computation time, because there is a delay, I will not be able to start backpropagation until I complete until the end. And the reason is very simple, right? Because the output at the last time step depends on the hidden values across all the time steps, right? So there is no way I can compute, so I need to compute the gradient of that output with respect, in order to compute it with respect to, let's say I have parameters W here in the transformation, from hidden layer to hidden layer. In order to compute the gradient of the output with respect to this W, I have to compute it with regard to all the time steps, right? So the effect of W on the transformation from H1 to H2, and then on the transformation from H2 to H3, and then from H3 to H4, right? So you have to unfold the whole computational graph before you start computing backpropagation. And that brings us to the advantage of type B network. And this backpropagation is called backpropagation through time, and then abbreviation is BPTT. Now, networks of type B, which are called networks with output recurrence, right? Here, the recurrence is happening from the output at time t to the hidden layer at time t plus 1. What's the advantage here is that I could decouple the different time steps. And the reason I could decouple the different time steps is that basically during training, instead of the output, so let's say I want to train the 10th time step. The 10th time step has an input from the output at time 9, right? Instead of using the output at time 9, I basically use the training label that I have corresponding to the 9th time step, right? And thereby I could parallelize the training, and I could parallelize the backward propagation computation across the different time steps. And this is what's called training with teacher forcing, and that will be the topic of the next video, right? So in terms of this video, before we finalize, now it's important, because if the loss function allows me, the loss function doesn't have a coupling between the different time steps, so allows me, basically the loss function at time t depends only on the input at time t, right? Then I could decouple the computation of the gradient, and I could decouple the training of the different time steps. So for long sequences, these networks with output recurrence, if trained with the teacher forcing mechanism, can be much faster than the networks with hidden to hidden recurrence. Now, what is one major problem with these networks with output recurrence is that the output, while the hidden unit, I have complete flexibility on deciding the state of the hidden unit, right? So that I can create a summary of the inputs so far. Remember in the last video we mentioned h of t will contain a summary statistic. In networks with output recurrence, you want O of t, the output, to contain a summary statistic. And this is problematic, right? Because the output has another objective, which is basically to mimic the target or the training label at time t. So now it's the same unit, the output here. I wanted to mimic the target training label, and at the same time, I wanted to create a summary statistic of the input so far. So because this is all what's going to the next time step. Right? So that becomes a problem in terms of the representation, right? So here, to summarize, the expressive power of type A networks is much larger, it's more powerful. Type A networks, they are backed by theoretical guarantees. Type B networks are much more computationally efficient, especially when parallel computation is possible. Thank you.